Greetings. In this lecture series, we are going to cover something called Morse theory. And this lecture series is titled Morse Theory with No Background. So this lecture series serves as a high-level overall conversational guide for introducing you to the beautiful subject of Morse theory. It is not a formal lecture on what Morse theory actually is, but it should give you some intuition on why we want to study this subject and what Morse theory is on a high level overview. So let's get started on the content. So before we can talk about Morse theory, we need to talk about something that all mathematicians and engineers love. It is the study of optimization. And we know that optimization problem is everywhere. What are some good examples, right? So, one very straightforward example I can think of is, going to work or going to school. So you can try to optimize the time for you to go from your home, your dorm, to your classroom or your workspace. And also you can optimize the money that you spend to get there, and many other things that you can optimize. And there is a common theme for these problems when mathematicians and engineers model those problems. Our objective is to first finding a cost function. And here we define what is being minimized or maximized there. And the second thing we want to do is we want to find the minimum or the maximum to solve this problem. So it is pretty straightforward in a intuition sense that for this going to work slash going to school problem, we have our cost function, which is the time spent or money spent or other things that you can think of. And finding the min slash max would be trying to minimize the time spent or minimize the money you spend. Or at the same time, you can also maximize something. For example, if you want to maximize the amount of time that you spend, um, for example, indoor when you go to your destination when you are walking because the weather is hot outside or something like that, right? But in a mathematical sense, what would some examples be like? Well, the easiest example I can think of here is a 2D example where you have x and y and you have a parabola. And in this function, we can clearly see that the minimizer is right here. And then we can extend it to a three-dimensional problem where we have x, y, and z. And now we have a bowl. And we have those little circles that are called level sets. And here we indicate our minimizer, which is where we are trying to get at. So as we can see, this problem can be as simple as a two-dimensional problem where we are just trying to find a minimizer on a line. You can also think of it as a one-dimensional problem where your search space is on the axis of x and your output is on your y, where we are trying to minimize y. And it can also be as complicated as on a surface of a particular mathematical object that looks like something like this bowl or something that's maybe really weird looking. And we're trying to find some cost that's we're trying to minimize such cost or maximize it. So here we can have a complex space. And now we are going to denote this as M. And here we want to find a function f of x that maps from this space that we just defined, let's say to a real number, and we want to find where the max or min are. So this is not a very, very rigorous definition of what an optimization problem is, but it should build some intuition for you. You have some surface or some shape, and we're trying to find the minimizer, the corresponding place in the entire state space where the corresponding value of such state gives you a lowest slash highest cost of interest. So now let's circle back to Morse theory. Why do we want to study Morse theory? Well, Morse theory actually focuses on two different areas of study. There's the first object, the objects of study in geometry. It is called spaces. And the other one, the objects of study in analysis. And those are called functions. And Morse theory, oops, misspelled Morse. Morse theory is the study of the relationship between functions on a space and the shape of the space. So those two mathematical objects of interest are basically what Morse theory is. We want to study functions and spaces where those functions operate on. So in particular, this feature is to look at critical points, which we are going to define rigorously soon. Somewhat rigorously, don't worry. We want to look at critical points of a function, and we want to derive information on the shape of the space from the information about the critical points. So in other words, let's look at this example here. If we know about this minimizer of this function, we can actually derive a lot of information about what this function is through just looking at this minimizer, looking at the property of this point. Isn't that amazing? You can actually think of so many benefit from this. For example, for data storage purposes, right? So for computer engineers, all they care about is try to store as much information as possible and try to use as little information as possible to represent something. So if you can just store a single point and this single point can construct the entire place, how nice is that, right? So basically, Morse theory also studies critical points to describe big spaces. So in order to do this, we will focus on this study of optimization in the context of these things. First, we're going to cover some analysis tools. This includes real analysis. So yes, real analysis is a very important course that I believe 99% of the engineers will need to take it, and you will actually your brain will grow like three sizes larger if you take this course because it really opens your mind to look at math in a very different way. And I think it's a pretty correct way to look at math. But yes, analysis is very important, and we are only going to cover some very, very rudimental things that you need. And we're not going into detail about the proofs, but it is important for you to know. And the second thing, we're going to cover a little bit about topology. Because after all, we're going to study shapes of spaces. And topology is a very important study too. It's also very, very abstract. And we're trying to make it very easy. After all, this course is built for people with no background in analysis and topology. And the third thing we're going to cover is differential topology, which is even more involved because we are going to talk about something called diffeomorphism, homeomorphism, those morphisms that kind of changes how some spaces look and finding correlations between spaces. And you don't need to worry about that for now. It all sounds very intimidating, but soon you will gain a lot of intuition about these. You don't need to necessarily be a math expert. This is a lecture series, again, let me reiterate, to help you understand some high level understanding of this subject matter and hopefully get you interested in this area of study. And at the same time, maybe um, help you to understand some high level things, not only for Morse theory, but also for optimization and just also some cool concepts about some elegant problems and how some spaces are constructed, etc. So yeah, um, basically, this is what we're going to cover. And let's jump into some definitions and let's start our main content now. So let's start our Morse theory introduction formally. And let's start by giving it the title Chapter 1. We're going to call this Morse theory on surfaces. And let's look at a definition. We're going to give it a heading 1.1. So as we talked about earlier, critical points are a very important concepts that are very involved in Morse theory. So we're going to give it a definition first. And I believe a lot of people have taken calculus and they probably have some understanding of a critical point is. And let's consider the easiest case possible. Let's just look at a single variable function. So consider y equals to f of x. And let's look at the derivative. So if at some point x naught, the derivative of f equals to 0, then it is a critical point. This is the definition of what a critical point is in one dimension. How easy is that? So basically, you take the partial derivative. Well, right now we only have one dimension, so we just take the derivative of f in respect to x. And at this particular point, we find that the value equals to 0, then it is a critical point. And we further notice that if we take another derivative, and if it's not 0, while this point is a critical point, then we can say that the point is a non-degenerate critical point. What does that mean? We'll illustrate soon. And if this value equals to zero, then it is a degenerate critical point. So if we look at the second derivative of this function at the point x naught, we can have two different types of critical point. One being degenerate, one being non-degenerate. They're actually very important in Morse theory studies because mostly we're going to focus on non-degenerate critical point, and we're going to see why very soon. So to gain some intuition, of course, we're going to give you guys some examples. So the easiest one, y equals to x squared. We can see that y derivative equals to 2x. And if we take the double derivative, we see that this equals to 2. And if x equals to 0, we say that y prime equals to 0, which we know that x equals to 0 is a critical point. And we can see that the double derivative is not 0. So we know that it is non-degenerative. Therefore, we got a non-degenerate point. And as we can see, if we have n greater or equal to 3, we will have critical point x equals to 0 for y equals to x to the n. For these classes of functions, we actually end up having degenerate critical points. And you can do this math on your own. I don't think I need to do this myself. You can kind of convince yourself that this is true, and also you can do this through induction, or you can just try it yourself. It's very simple, but basically that's what you get. And now, okay, these are just two examples, right? But what would these two properties really um, mean anything in this in our application slash like why would they matter, right? So they are actually very, very closely related to something called perturbation. So what happens when we perturb our function a little bit, right? So what a perturbation is kind of like you can think of it as injecting some noise or injecting a regularizer. Regularizer being like arbitrary function that you insert into your original function. So again, we're gonna do this example again. Let's look at our previous example, y equals to x squared. We already know it has a non-degenerative um, critical point. And let's add a linear perturbation, which will look like this. So we simply add this linear term, ax plus b, to this original function. And now we take the derivative. We end up having y prime equals to 2x plus a. And this implies x equals to negative a over 2 is the only critical point. So we conclude that after some perturbation, a non-degenerative critical point is still non-degenerative, right? So this example is pretty straightforward. And let's compare with a case of a degenerative one. So let's just make this polynomial to the power of 3. Because we know if n is greater or equal to 3, then the critical point becomes degenerative. So let's just make n equals to 3. And let's look at the cubic function. And at the same time, we still add the same perturbation, ax plus b. And let's take the derivative again. We have 3x squared plus a. And let's solve for what x is. When y equals to 0, we get x equals to plus or minus negative a over 3 in the square root. And we conclude that if a is greater than 0, we have no real solutions. So what does that mean? That means we actually lose a critical point. And if a is smaller than 0, we end up having 2 critical points. And these 2 points become non-degenerative. Pretty interesting, right? So here is what we can conclude from the earlier example. For non-degenerative critical points, we can call those as stable critical points because we can perturb them and their property doesn't seem to change. But however, when we have those degenerative points, we end up having unstable points that when we perturb them, their properties can easily change. And we don't know how they would change sometimes when the problems get complicated. Okay, next we are going to cover a new definition, which also is very important in the study of mathematics and engineering, and probably personally favorite concept. And it is called the Hessian. So now let's move on to a little bit more complicated function. Let's look at a real valued function, z. And now our function takes in two values, x and y. And x and y are both real numbers. By the way, for people that don't know these mathematical symbols, this little symbol means belongs or is a member of something. So interpret this as belongs to, oops. And here for R, this means real numbers. So basically, this just means that x and y are real numbers. They belong in the set of real numbers. And let's take a look at how this function may look like. So let's draw a coordinate system, x, y, and z. And let's draw a beautiful surface. And we have a point on this surface. Let's make it over here. So this point is z. And let's draw our xy plane for reference. And here, if we project this point onto our space, this becomes the xy location of where this value is. Great. So let's define Critical point in this context. Now we have two inputs in our state space. So the definition actually carries. Now let's consider a point P naught, which can be represented as x naught, y naught as a tuple in xy plane. It is a critical point of function z f of xy if the following two holds, the partial derivative of f in respect to x at point P naught equals to 0, and the partial of f with respect to y at P naught is also 0. And here we also assume that f is of class C, which this means it's smooth. And we're going to cover smoothness later very rigorously because it's a very, very important concept. After all, Morse theory is also a study of functions. And the properties of functions, one of them being smooth, is a critical ingredient. But we're going to cover that later. Don't worry about that. So let's look at one example to give you some concrete intuition. So the origin, 0, 0, is a critical point of each of the following. We have z equals to x squared plus y squared, z equals to x squared minus y squared, and z equals to negative x squared minus y squared. These are very simple examples, right? And I don't think I need to convince you that these are critical points. You can find the partial derivatives and plug in 0, 0 to convince yourself, right? And a critical point, P naught, is non-degenerative if it satisfies the double partial in respect to f is not 0, and its double partial in respect to y is not 0. This seems natural, right? This kind of seems like how we would want to define what a non-degenerative point is if we just import our definition from earlier, right? But this is wrong. This is not how we want to define this. Why is that? Well, if you are an expert in linear algebra, which I assume you might not be, even if you think so, I think you're wrong. You might want to think again. Because after some coordinate changes, which means we can do some linear algebra tricks to change our coordinates through some rotations. But don't worry about that. I would assume that you don't know about this concept if you haven't taken linear algebra, or if you've only taken one or two classes on linear algebra. But if you are familiar with this concept, good job. I think I actually personally learned about this coordinate transform a very long time ago, but when I actually understood it, it was probably my first year of grad school, which it's kind of late, but I would say that this is also one of the most important concepts that I understood, and I encourage you to go through the proofs for coordinate changes. It's very important, and it also has some topological slash, I guess, in analysis is also very important. There's this isomorphism concept that you learn when you talk about coordinate changes. But anyways, um, Yeah, this is just a detour to talk to show you how important this is, and in this lecture series, we are only going to talk about things in high level. So I'm not going into the details for that, but highly encourage you to go through that. So, what is the true definition of a non-degenerative point? What would you think? Oops, I can't spell. Let's just call it non-degenerative. Actually, it should be called non-degenerate critical point. But I am lazy and I don't want to erase it. So let's just stick with this. There we go. How should we define this? We are going to borrow this matrix concept. So suppose we have a point x naught, y naught, and it is a critical point of function z. And we call this matrix where we have all the second order derivatives in this matrix. We call such matrix, oops, sorry about that. We call such matrix evaluated at P naught the Hessian, just like how our title suggested. And of course, because we're evaluating at this point, this is the Hessian at the critical point, P naught. And we can also represent it as HF of P naught. So a critical point, P naught of function z, when is it really degenerative? It's a rhetorical question, of course, but you can sort of answer it on your own. And I kind of hinted you when I constructed this matrix, right? So if our determinant of the Hessian at P naught is not zero, in other words, our determinant, which is calculated with this almost cross product looking thing, right? This value is not zero. And as we can see in this case, our two matrices, I should probably use red. Our two entries in this matrix are the same. Why is that? They are actually not always the same. If you've taken real analysis, you would know why. But right now, let's just say that if a function is C2, this is sufficient to say that you have a symmetric Hessian, which is you can swap the order of taking partial derivatives. and you will get the same thing. And we've also considered all of our function maps to be in C infinity, which means you can take infinite many derivatives. So this satisfies this condition trivially. And let's just kind of stick with this and not focus on this detail of why this really is the case. But if you're really interested, you can look at when Hessians are not symmetric, or what is the necessary and sufficient condition for partial derivatives to be taken with without, the care of ordering. But there is a difference. The moral of the story, there is a difference between those two. But for our case, they are the same, just because we have a C infinity function. Okay, that was another detour. And we're going to give you a quick example, and we can call it a day for our first lecture. This lecture has gone quite long, I've realized, and apologize because this is my first time recording a lecture online, and I promise it will get better. And let's just reiterate this real quick. Our Hessian is symmetric because we have the C infinity property for our function. And let's look at an example of z equals to y squared plus y to the third. And let's compute the Hessian real quick. So real quick, let's look at this. If we take the double derivative of x, what is this? It's probably 2, right? Yeah, it is 2. Yeah, it's 2 wherever it is. But let's just label that we want to compute uh, the origins Hessian. And what about if we take the derivative of x first and then y? It's 0, right? And the same thing happens here. And for the last entry, we take the derivative of y twice, and we have 6y. And it is evaluated as 0, 0 again, which we will get this matrix to equal to 2, 0, 0, 0. And clearly, we can compute the determinant of this Hessian. So determinant of the Hessian becomes 2 times 0 minus 0 times 0, right? Which gives us 0. What does that mean? That means 0, 0 is a degenerate critical point, which also means it's not stable. We do not like this. So why do we not like this? We actually have a lot of things that we can say about a non-degenerative critical point. But for a degenerative critical point, it's actually really difficult to say something about it just because how unstable it can be. As we've shown earlier, for a one-dimensional case, we can make one degenerate critical point disappear or make it turn into two stable, which is non-degenerate critical points. So that's just one reason. Later, we're going to unfold the other reasons why this is undesirable. But right now, I think it is a good time to stop the lecture. And next time, we're going to start with the lemma. What the lemma is kind of a small discovery that uses to prove some big theorem. But this lemma is going to show you how useful critical points of non-degenerative critical points uh, are and how we can derive useful information from these. And of course, degenerate critical points are very useful, and there's a whole study on it. But we're also going to show that we are not going to care about them as much in the study of Morse theory, just because they don't give us things that we can say for certain. Okay, so this concludes the first lecture, and I hope you guys enjoyed this. And please share and subscribe to my channel if you are so generous and feel so inclined. And if you don't, I mean, I still really appreciate you watching this. This is my first time doing it, and I think it is really fun. And hope to see you next time.